Welcome back, Amherst. Today's May 12th, 2020, and we have 2 units remaining, redox and electrochemistry, and then organic chemistry. By my calculations, we've got about 2.5 weeks of instruction left. I think we're going to be finishing up in early June. So, this is an interesting unit. If you like puzzles, you'll like redox equations. If you don't, it might drive you a little crazy, but all is not lost. It's not that hard a unit. It seems hard at first, but it's just a method. So redox stands for reduction, oxidation. Okay? Reduction is the gaining of electrons. If you gain negative entities, your overall charge, your oxidation state is going to go down. That's why they call it reduction. Oxidation is the process of losing electrons, and if you lose electrons, you're losing your negative. You didn't lose any of your positives, so your overall charge increases. So it's a transfer of electrons. There's Leo. Leo was a cat. When my wife and I first met, we had an apartment in North Buffalo, and our neighbors across the street had a big old barn cat named Leo. Leo was a white cat with a black tail and a little goatee. He looked like Leonardo, so they called him Leo. Leo is the only cat, well, not the only cat anymore, but he's the first cat to ever come knocking on my door. So Leo showed up one day and knocked on the door, and I looked down. I had never seen this cat before, and he came walking in like he owned the place. I'm like, okay, who's this? And they said, oh, that's Leo. Leo was king of the neighborhood. Leo said, grr. Yeah, that's kind of goofy. Leo, notice this diagram? You make this diagram, you get these questions right. It's goofy, but Leo is written up, grr is written down. Leo says grr. What's going up, what's going down is the oxidation number. Leo stands for losing electrons. That's called oxidation. Your oxidation number increases. Grr, that's gaining electrons. That's reduction. Your oxidation number goes down. This goofy diagram makes all the difference in the world. Leo says grr, Leo says grr, Leo says grr. So what do you need to know about redox? Well, you can't have one without the other. Kind of like Love and Marriage, right? That Frank Sinatra song. If somebody's losing electrons, somebody else is gaining those electrons. There is no electron limbo in between. So it's a simultaneous process. Each one is called a half reaction. Oxidation is losing electrons. It's a half of the process. Reduction is gaining those same electrons. That's the other half of the process. It's a transfer of electrons. The 2 half reactions make up that one transfer. They happen simultaneously. Don't fall for those questions. It's a chicken-egg question. It's a non-answerable question. Which one happens first? Well, you can't gain an electron until you lose an electron, but you don't really have any intermediate. So as the electron is being lost, the electron is being gained, and it's a simultaneous process. All right? Not all reactions are redox reactions, but single replacement reactions always involve the transfer of electrons, and we'll deal more with table J later. But if it's a single replacement reaction, it is always a redox reaction. Synthesis and decomp, they're usually redox, but they don't have to be. If your oxidation numbers don't change, they are not redox, but usually those two are. But double replacement is never a redox reaction. You're simply trading partners, and you're not really transferring any electrons. You're just changing who the ions were with. So the most important thing I could say about this unit is this is a multi-step, kind of a puzzle process, and you have to get the first process right, and if you don't, it's all bad money after good, so to speak. You have to be able to assign oxidation numbers correctly. If you don't get the oxidation numbers correct, you could spend several hours on a problem working your way in circles, going, this problem doesn't work out. Well, yeah, it goes back to that first process. Now, a recurring theme in this unit is we're going to look at things one atom at a time. Subscripts can get a little bit messy, but if we consider them one atom at a time and then deal with them appropriately later, life gets better. Nothing in this world is free. You will have to pay the piper at some point. Those subscripts are going to become important, but we'll deal with them as we see fit. So let's go over some rules for assigning oxidation numbers. We've done this all this year. This is review at this point. But first thing you need to remember, people tend to forget this one, free elements. Elements that are not in compounds. Uncombined elements. They have a charge of 0. Their number of protons, the number of electrons are equivalent. So their oxidation state is 0. And it doesn't matter if they have a subscript. So if it's just sodium, not with anybody, it's 0. If it's one of the Hofbrinkels, diatomics, doesn't matter. Each chlorine atom here is neutral, it's 0. Oxygen, sometimes it comes in 3s, that's ozone, doesn't matter. If it's not combined with any other type of element, 0. Phosphorus comes in 4s. Okay? It doesn't matter, it's not combined with any other element. Free elements are 0. All right, let's talk about when you're in a compound. Fluorine, the greediest of all elements, the tiny little thug. In a compound, fluorine is always -1. It's the most electronegative element. It's going to get that electron, no exceptions. The second most electronegative element is oxygen. Oxygen is usually -2. It's got 6 valence electrons. It wants 2 more. But it's not always 2. About 99% of the time it's -2. But what if it's with fluorine? Fluorine had to be -1 for a total of -2 here. So I guess when it's with fluorine, oxygen is +2. And what if it's in a polyatomic ion called a peroxide? O2 with a total charge of -2, well, each of them is -1. So oxygen is almost always -2. In peroxides, it is -1. And when it's with fluorine, it can be +2. Those are the only times you're going to see oxygen do something different. Group 1 metals, they're going to be +1. Group 2 metals, they're going to be +2. Let's ring in some bells. I would hope so. Hydrogen's in group 1, but it's kind of separated. It's not an alkali metal. But if it's a free element, you know, H2, part of Hofbrinkel, it's 0. But in a compound, it usually is +1. But in a hydride, IDE there, hydrogen acting as nonmetal, it can be -1. Once again, about 95% of the time, it's going to be +1, maybe 99% of the time. But a hydride is when hydrogen finds itself with a really reactive metal from group 1 or group 2. So if I had, for example, sodium hydride or calcium hydride, hydrogen adopts a -1 nonmetallic profile. Sodium's group 1 +1, -1 balances that. Calcium is +2, well, 2 -1s would balance that. Now, we've been applying this rule already, kind of taken for granted, but the sum of the oxidation numbers for a compound adds up to 0. So sodium chloride, sodium +1, and chlorine -1, they add up to 0. The sum is going to be 0. What if you're looking at just part of a compound, like a polyatomic ion? Well, if you add up the sum, they equal the charge on that polyatomic ion. What does that mean? That simply means, for example, if I had sulfate, SO4 with a charge of -2, they're going to add up to -2. So if I take sulfur and oxygen, well, oxygen likes to be -2. There are 4 of them for a total of -8. So what -8 gives me -2? Well, sulfur must be doing +6 in this case. We've done this stuff. I know it gets a little confusing, but it bears repeating. All right. Sometimes you're left with choices. Well, the more electronegative element, the more nonmetallic element, the one that's higher on the periodic table or more off to the right, that's the boss. They get to do their favorite thing. They're more electronegative. So the ones that are written last in the compounds in the formula. So if I have, for example, carbon with sulfur, well, sulfur is more nonmetallic than carbon, so it's written last. Sulfur is the boss here. It gets to do its favorite oxidation state. So if I go to the periodic table and I look up the oxidation states, sulfur's favorite oxidation state is indeed -2. So I assign sulfur a charge of -2. There are 2 of them for a total of -4. Carbon must do a +4 oxidation state to make that sum equal to 0. Okay, the second one is the boss. The more nonmetallic is the boss. They get to do their favorite, what I'll call favorite oxidation states, the ones written first on the periodic table. Now, let's just look at this for a second. Carbon's got electronegativity 2.6. Sulfur's got electronegativity 2.6. That's a nonpolar covalent bond. They would be sharing electrons. They'd be sharing them equally. This whole notion of electrons are transferred to adopt these oxidation states, that's not true, but it's a model we employ. It still works. It's going to allow us to consider when electrons do get transferred, what's going to go on there. It's a complex process. Even though this looks like maybe it was ionic, it's not. We're sharing electrons, and in this case we're even sharing them equally, but we're going to employ the notion of electron transfer as a model to get more things done. So let's do a couple examples of assigning oxidation numbers. Here I have a binary salt. It's a metal with a nonmetal. Well, the nonmetal's the boss. chlorine's favorite thing is -1, and that works out pretty well because calcium's in group 2 and has to be +2. So in this case, calcium's in the oxidation state of +2, chlorine is in -1. Now, in this situation, this is the important number. It's what each atom is doing. You don't care so much about the subtotal. The important number here is the -1. Here's water. Well, oxygen likes to be -2, and hydrogen likes to be +1. For a total of +2, yep, that would balance out to 0. And once again, this would be the important number. Easy peasy. What if I have a polyatomic ion? I see CuSO4. Well, I have a rule for oxygen, but I don't have a rule for sulfur, and copper could be +1 or +2. So what am I supposed to do here? Well, table E tells me that sulfate has a charge of -2. That's going to force my hand and say, all right, well, copper must have been in the +2 state. They add up to 0. But now what? Okay, well, sulfur and oxygen combine in sulfate to be a total of -2. Oxygen likes to be -2. 4 times -2, that's -8. Okay, well, sulfur must have been +6 because 6 minus 8 gives me -2. So in CuSO4, copper's in the +2 state, oxygen's in the -2 state, sulfur's in the +6 state. What if I had something like lead with sulfite taken twice? All right, well, lead could be +2 or +4. I know that sulfite, SO3, has a charge of -2. There are 2 of them. That's a total of -4. That tells me lead is going to be in the +4 state. And then I'm going to look inside sulfite, SO3, adds up to -2. Oxygen likes to be -2. That's a total of -6. What minus 6 gives me -2? +4. So in this case, lead would be +4, oxygen would be -2, and sulfur would be +4. It's really important that you get each individual atom correct. Here's a big old gnarly looking one. Ammonium dichromate. Wow. All right, well, I see this polyatomic ion, ammonium, and I see this polyatomic ion, dichromate, and table E tells me ammonium is +1, that's a total of +2, and dichromate was a total of -2, so I guess that worked out, except I still don't have any of my individual atoms. So let's look at these polyatomic ions one at a time. Here's NH4, it's written kind of backwards, it's weird, hydrogen usually goes first, but it doesn't in this case, but it adds up to a total of +1. Okay, hydrogen likes to be +1, that's a total of +4, so I guess nitrogen in this case is -3. That would work out. And dichromate, Cr2O7, turns out to be a total of -2, according to table E. All right, oxygen likes to be -2, that's a total of -14. So what minus 14 is -2? Well, +12, you say. But there are 2 chromiums. All right, well, that's all right. Each chromium would be then +6. 2 at +6 would give me 12. So in this monstrosity known as ammonium dichromate, nitrogen was in the -3 state. Hydrogen was in the +1 state. Chromium was in the +6 state. And this oxygen over here was in the -2 state. Those are the important numbers, what each one is doing. Now, you have to be able to get those correct each and every time without fail. There is no margin for error in assigning oxidation numbers. So part of your homework tonight is going to be practice in assigning oxidation numbers. So we're going to go to our redox packet, and you're going to do worksheet number 2, front and back. Now, I'll just give you a little heads up. Numbers 21, 25, and 26, those are oddballs. That's where they're doing weird things. You've got a peroxide here, you've got OF2, you've got a hydride there. I gave it a scan earlier. I don't think there are any other oddball ones on this page, but on the back page, numbers 14, 15, 16, and 17 are similar. You've got a hydride, peroxide, hydride, peroxide. Okay, so they're a little bit scattered in there, the oddball stuff, but that's just part of your homework. trust me, it's just beginning. Okay, oxidation numbers, that's a start. Now, I'm going to move forward because I think if you get that and it is review, that's about 3 or 4 minutes of homework and then you're done. So let's move on to cutting to the chase. We're going to balance a redox reaction here. This is really the point of the first half of this unit. Now, in this electron transfer method, it's all about getting the electrons lost equal to the electrons gained. They are indeed the same electrons. Sometimes you can look at an equation and you can balance it, and you don't have to go through the multi-step process of the electron transfer method. For example, if I look at aluminum plus oxygen forming aluminum oxide, aluminum's free element starts as 0, oxygen's free element starts as 0. In a compound, this turns out to be +3 and -2, and you go, oh, this is a redox reaction, and I can find out what changed, and we'll explain this in great detail, but I could probably just look at this and balance it and say, well, look, I've got aluminum and oxygen, I've got one of these, and I've got 2 of those, and I've got 2 of these and 3 of these, and go, well, it's a 3-2 situation, make those both 6, put a 2 here, that'll give me 6 oxygens, put a 3 here, that'll give me 6 oxygens, and this 2 gets distributed to give me 4 aluminums, 4 aluminums. We've done this stuff, right? Sometimes you can just look at it and balance it. So if it is one of those situations, indeed, there might be some points to be had for identifying some parts of the process here, but you'll find it's just easy to just balance it. But what if your equation is a little bit more gnarly? Take, for example, this equation. I've got potassium dichromate plus iron 2 sulfate plus sulfuric acid goes to, this looks like chromium and what's it, +3 sulfate and potassium sulfate and iron 3 sulfate and water. Wow, they've got 1, 2, 3 reactants and 1, 2, 3, 4 products, and that just looks big and nasty. That wouldn't balance very well by inspection. If I go to worksheet 5, indeed, this is number 9. So there is not nearly enough room to get these problems done here. You're going to want your periodic table and you're going to want some separate paper because this is a multi-step process and we're going to get most of it done today. So we're going to do this example and I'm going to assign one more problem from there for homework. Alright, so step 1, assign your oxidation numbers. Once again, if you get those wrong, you've got like 7 or 8 more steps, and if you get the first one wrong, it doesn't work out, so there's 0 margin for error there. So here we go. Potassium's group 1 is going to be +1. There's a polyatomic ion for -2. Alright, I'm going to break into that polyatomic ion momentarily and take a look at it. Sulfate is -2. That tells me iron is +2. Once again, I'll break inside there momentarily and look at it. Sulfate -2, hydrogen +1 for a total of +2. Okay. Sulfate -2, that's -6, I need +6, so I guess chromium here, there are 2 of them, each one's going to be +3. Potassium group 1, +1, sulfate -2. Sulfate -3, -2, -6, I need +6, same kind of deal. 2 irons, each at +3. Hydrogen +1, oxygen -2. Now, that's a lot going on right there. What I just did in 10 seconds, that might take a few minutes. That's all right. Let's break inside this polyatomic ion. Cr2O7 is dichromate. It adds up to -2. Oxygen likes to be in a charge of -2. That's a total of -14. So I'm going to need 12 minus 14 to give me -2. Chromium was +6 here. That's the important number. All right, let's look at our sulfates. We had a lot of sulfates going on here. It was just all over the place. Sulfate is a charge of -2. Oxygen likes to be -2. There are 4 of them. That's -8. And 6 minus 8 will give me my -2. So in these compounds here, the important thing is what is each atom doing? Potassium was +1, chromium was +6, oxygen was -2, iron +2, sulfur +6, oxygen -2, hydrogen +1, sulfur +6, oxygen -2, chromium +3, sulfur -6, oxygen -2, potassium +1, sulfur +6, oxygen -2, iron +3, sulfur +6, oxygen -2, hydrogen +1, oxygen -2. Those are the important numbers. Now I know I'm a little bit off screen here, but you get the point. Take your time here. This is important. There is 0 margin for error in assigning oxidation numbers. If you don't understand that, stop, ask me questions, but make sure you get that right. If you don't, it's bad news from here on out. It's tough to recover any points. Step 2, look for what changed. If none of the elements changed their oxidation state, it's not a redox reaction. But indeed, you will find somebody moved up and somebody moved down. Okay? Consider the individual atoms, not the subtotals. I'm not interested in the +2 here, for example. I'm interested potassium is +1. Well, okay, potassium stayed +1. Potassium was not involved in redox. Look at the individual oxidation states. So here they are. Look at this. Chromium started at +6. Chromium ended at +3. That's definitely a change. Matter of fact, going from 6 to 3, that's moving down. That's a reduction. So chromium got reduced from +6 to +3. Iron started at +2. Iron ended at +3. That's actually moving up. 2 to 3 is moving up. That's Leo. That's oxidation. So I've identified my reduction and my oxidation in this equation. Nobody else changed. Potassium stayed at +1. Oxygen stayed at -2 the whole way. Sulfate, for that matter, every time I see sulfate, sulfur is +6, oxygen is -2, +6 minus 2, 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 and oxygen over here, again, -2. It didn't change. Hydrogen +1, hydrogen +1. Nobody else was involved in redox. Okay, so once you've identified who changed, write your half reactions. Half of the process is reduction, half of the process is oxidation. The order in which you write them doesn't matter, but here's an important thing. We're going to pay the piper later. As opposed to paying up front, we're going to do it at a later step. So I am not interested at this point in subscripts. Yeah, chromium's got a subscript of 2 here. I don't care. I'm interested in each chromium being +6. Okay, here's one iron, no big deal there. Here's, once again, subscript. I'm going to worry about that later. Here's a subscript. I'm going to worry about that later. So one atom at a time. This is going to be a recurring theme. All right, so here are my half reactions. Chromium started at +6. Chromium ended at +3. I guess I had to gain 3 electrons. 3 negatives with the 6 positives will take me down to 3 positive. And oxidation, iron started at +2. Iron ended as +3. Now here's the thing. Oxidation, electrons go over here on the other side of the equation. Let me say that again. In oxidation, you write your electrons on the other side of the equation. To go from +2 to +3, you had to lose 1 electron over here. Leo, electrons go on the other side of the equation over there. Electrons are gained for reduction, they're on the left. Electrons are lost for oxidation, they're on the right. Okay, well, how do you gain 3 electrons if only 1 was lost? You have to get those equal to each other. So your next step, they are the same electrons. Get your electrons lost equal to your electrons gained. If there are 3 electrons here, only 1 here, I'm going to multiply my oxidation half reaction by 3. Now I'm going to distribute that 3 to the coefficients out in front of each of the players in this game, not the charges. I'm not changing the charge of the electron. I'm not changing the charge of the ion. Take this 3 and put it out here, put it out here, put it out here. So my reduction didn't change. Chromium +6 and 3 electrons goes to chromium +3. But now I've got 3 irons in the +2 state and 3 irons in the +3 state and 3 electrons, and I've got 3 electrons here and I've got 3 electrons here, and I've made them equal to each other. Life is getting better. Combine your half reactions to get the net ionic equation. You know, the knights that go, nyeh, the electrons are going to cancel out. So we're going to add everything on the left and everything on the right. I'm just going to list them all out. Chromium +6 plus 3 electrons plus 3 iron +2s go to chromium +3 plus 3 iron +3s plus 3 electrons, and indeed my electrons cancel out, and my net ionic equation is 1 chromium +6 and 3 iron +2s go to 1 chromium +3 and 3 iron +3s. That's the part of the equation that is important. That's the redox portion of the equation. Everybody else was just a spectator ion, and there were plenty of them, but this is where the work is getting done. Now, I need to somehow incorporate this back into my original equation, but this is where you're going to need a little of what I'll call moxie. You got to pay the piper somewhere. We got up to this point by ignoring our subscripts. Sometimes you don't have to worry about this. Sometimes it goes in nice and easy, but sometimes it doesn't. If I look back at my original equation, chromium here had a subscript of 2. Chromium here had a subscript of 2. Iron here had a subscript of 2. Over here wasn't a big deal, it was just 1. Well, if I need 2 chromiums, I only have 1 here, that's not going to work. 3, that's not a problem. I could just put a 3 out there, but it's already messed up with this. 1 chromium here, I've got 2 chromiums here, it's not going to work, and 3 chromiums here, and they come in pairs. That's not going to work. So the easiest thing I can think is, well, I'm going to need at least 2 chromiums, so I'm going to double everything in my net ionic equation. I'm going to take everything here and multiply by 2 and see what happens. So same kind of process, distribute it out. You're not changing the charges, you're changing the coefficients out in front. So you're going to need 2 chromiums in the +6 state, and then 6 irons in the +2 state, and 2 chromiums in the +3 state, and 6 irons in the it's not supposed to be the +6 state, that's supposed to be the +3 state. See, this is very easy to get messed up. You need to be careful. So these are the numbers that I'm going to need to make this work out in the context of my original equation. All right, well, I need 2 chromiums in the +6 state. I'm not going to put a 2 out here. I'm just going to put a 1 out there. That would account for both of them. I need 6 of these irons in the +2 state, so I'm going to put a 6 out in here. They only come in 1s. I need 2 of these chromium +3s, so I'm going to put a 1 out there. That would account for both of them. And I need 6 iron +3s, so I'm going to put a 3 out there. The 3 out there makes all the difference, because 3 times 2, that'll give me 6 of them. So I've gotten to the point now where at least I have 2 chromiums and 2 chromiums and 6 irons and 6 irons. And that's the hardest step for people to get when you have situations like this. I purposely chose a fairly difficult one to start with. Now, step 7 is the last of the important steps. You're going to balance everybody else, the spectator ions, like we've always done by inspection. You're going to make a list, okay? Also, I notice I've got sulfate here, I've got sulfate here, I've got sulfate here, I've got sulfate here, I've got sulfate here. Sulfate was not involved in redox at all. I'm going to treat it as one entity. So, with the coefficients that I have here, I'm going to take inventory. Players in the game: potassium, chromium, oxygen, iron, and I'm treating sulfate as one thing, and then hydrogen, and then sulfate again. So I've got 2 potassiums, yep. I've got 2 chromiums, okay. I've got 7 oxygens there, cool. This 6 gets distributed, so I have 6 irons and I have 6 sulfates there, 2 hydrogens, and another sulfate for a total of 7 sulfates there. Keep moving across. 2 chromiums, yep. 3 sulfates there, yep. 2 potassiums, another sulfate, 3 times 2, 6 irons, 3 times 3, there are 9 more sulfates there, 2 hydrogens, and 1 oxygen. Now you'll notice right off the bat, it's a good thing that the chromium and the iron are balanced, because that was the whole point of doing the first 6 steps. The order in which you go at this point doesn't really matter. Here's a hint. This doesn't always work, but it works often, works for me. Water is often one of your products. There's a whole other method on how to balance these equations called the ion-water method. We're not going to talk about that. But this oxygen is often the key. Not always, but usually for me. I'll start there. It doesn't really matter when these are all interconnected, but if I get that oxygen to balance, usually it works out pretty well. So I have 7 oxygens on the left-hand side of the equation. I'm going to need 7 oxygens over here, so I'm going to put a 7 out in front here. That 7 gets distributed, so it fixed my oxygens, but now I have 14 hydrogens. So I'm going to need 14 hydrogens over here. Well, they come in pairs. I'm not going to put a 14 out there. I'm going to put a 7 out there. That would give me 14 hydrogens. But indeed, it gets distributed out to that sulfate. So I had 6 sulfates over here, and now I'm adding on 7 sulfates. So now I've got 13 sulfates. Well, that's good, because that's what I needed. So I've got 2 potassiums, 2 potassiums, 2 chromiums, 2 chromiums, 7 oxygen, 7 oxygen, 6 iron, 6 iron, 13 sulfates, 13 sulfates, 14 hydrogen, 14 hydrogen. I am indeed balanced. The coefficient here is 1. Here's a 6, here's a 7, here's another 1, here's another 1, 3, and 7. So we balanced a fairly complex redox reaction. All right, that is what we're going to do for a couple days. So your second part of your homework tonight, let's assign one, maybe a little bit lesser difficulty, but I want you to go through these same processes. Just do for me number 1. I want you to do it like those processes, like what we just did with all those steps. All right. So homework tonight, you're going to assign some oxidation numbers. This should not take you that long. And then you're going to skip over to worksheet 5 and you're going to do number 1. All right. Enjoy. Take care.